is obtained at the output. Full wave rectifiers. In the full wave rectifier we will have two rectifiers. One is center tapped transformer, full wave rectifier, and other is bridge rectifier. First we'll see the center tap transformer full wave rectifier. There is two differences in these two rectifiers. One is the difference in the circuit, and other is peak inverse voltage difference, and one more difference is there is transformer utilization. So we'll see all the things in these two rectifiers. First we'll see center tap transformer full wave rectifier. This is the primary side of a transformer, and this is the secondary side of the transformer. These are the two diodes which will operate in different half cycles. This is the load resistance RL. And the secondary of the transformer will be tapped, grounded from the center. So it will be divided into two parts. One is this and one is this. This is the input voltage V1 and this is the output voltage V2. Now in this circuit, during positive half cycle of input, the polarity of the input will be like this. So by seeing the polarity, we can easily say that the diode D1 will be forward biased and diode D2 will be reverse biased here. So during positive half cycle, D1 is forward biased and D2 is reverse biased. If D1 is forward biased, it will be replaced by a short circuit, while D2 will be replaced by an open circuit. The current through this circuit will flow in this direction and a voltage drop will obtain across this load resistance. This is the input voltage with maximum value Vm and output voltage will be plotted here. During positive half cycle we are getting the output due to the conduction of diode D1. Now during negative half cycle, the polarity of input will be changed. Polarity will be like this. By seeing the polarity, we can easily say that this time diode D2 will operate and diode D1 will be reverse biased. So here D1 was operating during the negative half cycle. Diode D2 will operate and it will be replaced by a short circuit, while diode D1 will be replaced by an open circuit. Now in this second half cycle, the current through the circuit will be like this. Again the current is flowing through the resistance in the same direction. So during negative half cycle also we are getting the output in the same direction or with same polarity. So for full wave rectifier we are getting the output with the waveform shown in the figure. If the maximum value of this input is Vm, for this input waveform the DC value VDC equal to 0 volt because it is oscillating around 0 volts, and the RMS value is defined again will be equal to Vm by root 2. For the output voltage, the DC value will be non-zero, and this DC value is equal to twice Vm upon pi, that is double of the DC value in the half wave rectifier, and the RMS value will be same as the RMS value of input, that is Vm by root 2. Now for this full wave rectifier, we'll define the ripple factor. Ripple factor is root of RMS upon VDC whole square minus 1 is equal to under root of RMS value is Vm by root 2 whole square divided by twice Vm upon pi whole square minus 1 will be equal to under root of Vm will be cancelled, and it will be pi square by 8 minus 1, and it will be 0.48. So ripple factor is 0.48, and for half wave rectifier it was 1.21 volt. Here the ripple factor is less than the ripple factor of half wave rectifier, so it will be said that this rectifier is better than the half wave rectifier. Now next we will calculate the efficiency. For efficiency, first we will calculate the output DC power. Output DC power will be equal to IDC square into RL will be equal to twice Im by pi into RL, while input AC power will be equal to I RMS square into RS by 2 will be taken only because half of the winding is used at a time, plus RF plus RL will be equal to Im by root 2 whole square, this here also whole square, into RS by 2 plus RF plus RL. Now the efficiency will be twice Im square by pi, twice Im by pi whole square into RL divided by Im by root 2 whole square into RS by 2 plus RF plus RL into 100%. This Im square will be cancelled, and here we get 8 upon pi square into RL upon RS by 2 plus RF plus RL into 100%, and it comes out to be, so sorry, we don't know the RS, RF and RL. So for maximum efficiency, we have RS equal to RF equal to 0, so N max will be equal to 8 upon pi square into 100% will be equal to nearly 81.2%, that is double of half wave rectifier. So the efficiency of full wave rectifier is double of the half wave rectifier. In the full wave rectifier, 80% of the input power is obtained at the output. Now the next is peak inverse voltage, PIV. This is the secondary part, and these are the two diodes. Load resistance RL. Now when input is in positive half cycle, we know that this diode is forward biased and it will be replaced by a short circuit, while this diode is reverse biased because cathode is at higher potential with respect to anode. This kind of voltage will appear across this. When this diode is forward biased, a current will flow through the load resistance and will obtain a voltage across this diode, this load resistance. Now during positive half cycle, this diode is reverse biased, and if input is at its maximum, the current through load resistance will be maximum. Current through load resistance will be maximum. Also the voltage obtained across the load resistance will be maximum. So now if we apply KVL in this loop, we can calculate the peak inverse voltage across the diode. Now when input is maximum, there is it is assumed that there is no voltage drop across the diode, so all the input voltage will drop across the load resistance. And when input is at a maximum value, the inverse voltage or the reverse voltage will be at maximum across this diode D2. Now when we apply KVL in this loop, we start with plus Vm minus PIV plus Vm equal to 0. So PIV equal to twice Vm. The peak inverse voltage, that is the maximum voltage that appears across the diode when it is reverse biased in a full wave center tapped rectifier, is twice Vm, means the twice of the maximum value of input voltage. So it is the twice to that of in case of the half wave rectifier, which is the biggest disadvantage of this center tapped full wave uh, rectifier. If we apply an input voltage with 10 sin omega t, so the voltage across the diode will be 20 sin omega t. So for 10 volt maximum input, we should use a diode which should have a maximum 20 volt, which can sustain a 20 volt across it when it is reverse biased. It should not enter into breakdown. Also it should not be damaged, otherwise it cannot be used as a rectifier in the circuit. Next is transfer characteristics. Transfer characteristics very simple. We know that if Vi is greater than 0 volt, then diode D1 will be forward biased and diode D2 will be reverse biased, and will get an output which is equal to input Vi. And when input voltage is less than 0 volt, we get the D1 reverse biased and D2 operating, that is forward biased. And by seeing the waveform, suppose this is the input waveform and this is the output waveform, we know that the during negative half cycle, the input voltage is negative but the output is positive, so output is equal to minus Vi. Output voltage equal to minus Vi. Now we'll draw the transfer characteristics for this circuit. Break voltage is 0 volt. For Vi greater than 0 volt, output equal to input, so a positive slope straight line passing through origin. For Vi less than 0 volt, V naught equal to minus Vi, means a negative slope straight line. Negative slope straight line will be like this. This for this equation is V naught equal to minus Vi. For this equation, V naught equal to Vi. So these are the characteristics of a full wave rectifier. Next is bridge rectifier. Bridge rectifier is also a full wave rectifier. So the many of the characteristics that we have studied in the center tap transformer full wave rectifier will be same for the bridge rectifier, like efficiency, ripple factor, peak inverse voltage will be different, and the transfer characteristics will also be same for this bridge rectifier. First we'll see the basic circuit diagram. This circuit diagram is already asked in the GATE examination. Now in this bridge rectifier, at a time the arrangement is made like that. At a time two diodes will be conducting and we will get output across the load resistance. Here we are getting the secondary voltage at the secondary of this transformer. Now during positive off cycle, during positive off cycle the polarity will be like this, and by seeing the polarity we can say that this diode D3 diode D4 will be conducting, and if diode D3 and D4 will be conducting, so these will be replaced by short circuit, while the other two diode D1 and D2 will be replaced by open circuit. Now the current through the circuit will flow like this. Direction of current through load resistance is important. This way the current is flowing. So during positive off cycle we are getting an output. This is the input sinusoidal waveform. During positive off cycle we are getting a sinusoidal output during positive off cycle. This is the input voltage or voltage V2, and this is the output voltage across the load resistance V0. Now during negative off cycle diode D1 and D2 will be operating, while diode D3 and D4 will be reverse biased. So during negative off cycle, when the polarity of input voltage is like this, diode D1 and D2 are operating, so the current through circuit will be flowing like this. And again we can see that the direction of current through the load resistance is all again in the previous case as in the previous case. So we are getting this kind of output. For this the input is a full sinusoidal voltage. For this VDC equal to 0 volt and RMS value is again Vm by root 2, and the output waveform is full obtained for both the off cycles, and for this the DC value is VDC equal to twice Vm upon pi, and the RMS value is Vm by root 2. Again the RMS and DC value of output are as in the previous case, so we'll get the ripple factor are equal to again 0.48. Efficiency will be obtained again, maximum efficiency will be obtained again 81.2%. Peak inverse voltage we will calculate, it will be different from the previous case. Now if input is with the polarity shown, these two diodes D3 and D4 will be conducting while D1 and D2 will be reverse biased. So these will be replaced by an open circuit, while these two diodes will be replaced by short circuit. These will be replaced by short circuit while these two diodes will be replaced by open circuit. If these two diodes are open circuit, which means they have voltage across that them like this, and voltage like this across this diode. Now when input is with this polarity, the current through the circuit will flow through the path, and there will be a voltage with the polarity like this across this load resistance. Now when input is at its maximum, the voltage across the diode, reverse voltage across the diode will be also be maximum, that is peak inverse voltage, and also the voltage across load resistance will be Vm. Now if you apply KVL in this loop, we can calculate the peak inverse voltage across the diode. Again, see again the loop. If we apply KVL in this loop, we can calculate the peak inverse voltage. We start from here, we get minus Vm plus PIV minus Vm plus PIV equal to 0. So twice PIV equal to twice Vm. So PIV equal to Vm. So here only Vm voltage is appearing across the diode when it is reverse biased. So it is the advantage of this bridge rectifier over the center tap full wave rectifier. The Now in the half wave rectifier, the output waveform and input waveform are like this. This is the waveform of output of a half wave rectifier like this, and for full wave rectifier the waveform is like this. Now for this, if input frequency is f, then output frequency, that is ripple frequency, it is called ripple frequency, it is completing one cycle in this period of time, and also this output is completing one cycle, means repetition start from here, so it is also starting from the same point. So the ripple frequency is equal to the input frequency. But for the output of a full wave rectifier, here again repetition is started from here also. So the ripple frequency in a full wave rectifier is fr is equal to twice f, because time period is half, so frequency is double. So frequency, ripple frequency for a full wave rectifier is double that of input frequency. Now one example, say one example. For the waveform v of t equal to 2 plus cos of omega t plus pi by 6, the ratio v RMS to v average is, options are 3 by 2 root 2 pi root 3 by 2 and pi by 2. Now for this waveform, the given equation, we know that VDC equal to 2 volt and VAC RMS equal to Vm by root 2, which is equal to 1 by root 2. Clearly seen that 1 cos omega t plus pi by 6. This phase does not change the RMS or DC value of the output. Now remember that sinusoidal cosinusoidal waveform will be like this, and the DC value will be this 2 volt, and this will be the reference voltage 0 volt. Now the total RMS value for this will be under root of VDC square plus VAC RMS whole square will be equal to under root of 2 square plus 1 by root 2 square will be under root 4 plus 1 by 2. It will be under root 9 by 2. Now the ratio of VRMS to V average means VDC. Ratio of VRMS by VDC will be equal to under root 9 by 2 divided by 2 will be 1 by 2 under root 9 by 2. This 9 can be taken out, so it will be 3 by 2 root 2. Option A